Hello and welcome to our walkthrough of this worksheet from 7 for the side splitter theorem. It's very important we know the difference between using the side splitter theorem and using similar triangles. And you'll see that in a couple of these examples. I'm not going to go over all of them. I'm just going to go through some of them. And this first part is strictly just identifying proportional parts and which parts to use when you're creating these proportions. So this is straight up side splitter theorem. You could see that there are a number of parallel lines here. And when we have parallel lines and two transversals or more going through them, it creates proportional parts or proportional segments. So looking at this is just becomes pretty much a matching game. So A over C is proportional to or equal to blank over F. And we want to just find the missing piece which corresponds properly to A. And that would be D. So that's all we have to fill in here. So D over F is the proper proportion. Okay, let's take a look at 3. Follows the same idea. Blank over C is proportional to E over F. And we can see that the missing piece here is B, because that's a segment that lies between the same parallel lines as E, and all we have to do is put a B in that numerator. And let's just do number 5 for extra practice. A over B is proportional to blank over E, and that missing piece is in fact D. Okay, so setting up the proportion, being able to write the proportion is very important to working through these problems out, because when you actually have values in them, it makes it a lot easier. So for instance, in this particular case, we could actually use the side splitter theorem, and notice that it does make a triangle. And I'm going to show you that you can actually use similar triangles and the side splitter theorem here. In this particular case, though, the side splitter theorem is significantly better, because if you look, these are all sides or parts of sides to these triangles. So I personally would go just 24, which is the left side, over 10, and it pretty much writes it for you if you kind of look at this parallel line as a giant fraction bar. This now reads 20, it could read 24 over 10 is equal to, and then you could continue off on the other side, that's another your fraction bar, 12 over x. Okay, and just doing some cross multiplication, we get 24. X is equal to 120. Divide both sides by 24. And x is equal to 5. And you might have actually already noticed this, because how do you go from 24 to 12? You divide by 2. So you do that same idea, and x should be equal to 5 that way as well. So you definitely could do it that way if you recognize it. I'm also going to show you how to do this with similar triangles, just in case you're wondering. Let's do this red triangle, and then this smaller one is, the big one's the blue, the small one is the red, and let's do some math. Red triangle, it's a length of 24 and a 12. Now the blue part is actually A at the very tip top, the vertex, and D. And that length is not 10. That length is 24 plus 10, so that makes this 34. Okay, and then AC has a length of not just x, but 12 plus x. Okay, so when we're writing these proportions, you know me, I like to do these from left to right and do them proportionally. We should have 24 over 34 is equal to 12 over 12 plus x. Now, if you notice this will make this actually a very easy problem. Both of these values go into 2, or divide into 2 divides perfectly into them. So we could actually simplify this to 12 and 17. If you notice, after the fact, the numerators are exactly the same. meaning in order for these to be proportional, the denominators have to be equal to each other. So this actually becomes a straight problem where we have 17 is equal to 12 plus x minus 12 minus 12, and we should get x is equal to 5 from that, and we could see we get the same answer. Okay, so you can use similar triangles here as well, but personally I would say the side splitter theorem is better. Number 8 I'm not going to go over. Number 9 I definitely will though, because this can be interpreted as, oh, so this could be side splitter, but you have to be careful, and it says so. Be careful. You might want to fill this in first. ABE, let's highlight it. ABE, ooh, I said highlight. ABE is similar to what triangle? And we're highlighting it. ACD. So let's fill that in. ACD. This can make a big difference because when you write these proportions out, for instance, if I wrote EB is proportional to, it's EB, CD. And then doing this again, using the parts that are given in this problem, we want to work with the triangles. AE, EB was on the small one, so we have EB. So we'll go AE is the blue. AE, yep. And then AD, so AE is the first and the last. And then go over AD, that is also the first and the last of the second triangle. So this is your proportion. Let's fill in the actual values. EB has a length of 5. DC or CD has a length of 20. This, which could be simplified, we'll do that in 1 second. AE has a length of Y. AD has a length of 4 plus Y. So you have to be careful here, okay? Because it's the entire length, not just 4. So you have to make sure you're using that full length. So let's simplify this really quickly. 5 goes into both 5 and 20, so this becomes 1 over 4. From here, we should cross multiply. 4 multiplies with 4 plus y. 4 multiplies with y. Sorry, I said 1 time gets multiplied with 4 plus y. We should get 4 plus y is equal to 4y. Minus y from both sides. And you should get 4 is equal to 3y. Oops. Divide both sides by 3. And y is equal to 4/3. Now, you might be scared off by a fraction answer. This is perfectly okay. If you actually plug this in, you will find that the proportions will work out very well. If you don't believe me, try it out. Oh, we forgot to do this part. These are, in fact, similar by angle. Because if you remember, we have parallel lines, and when you have parallel lines, corresponding parts are, in fact, congruent. And they both actually have that angle A in them. So it'll be congruent through angle, or angle. Or, yeah, similar, I should say. So a lot of these are actually the same idea. I do want to stress this, though. When we're working with side splitter versus similar triangles, the difference is the base, okay? In number 7, both, when we're looking at the parallel lines in particular, the sides are the ones we're working with, okay? In number 8, the difference is one side is given, but the bases are also given. So when you're working with the bases are used, you want to use similar triangles to solve. Okay? So that is the big difference. Okay? Number 10, you should be able to determine, is this side splitter or is this similar triangles? Same thing for 11, 12, and 13. Right? So with that said, give these a try. and I'll post just the answer, the key to these particular problems. And I'll see you in the next